My name is Oliver Cawdell. I work at a small lab in Northern California called Vista Analytical Laboratory. And I'm here today to talk about PFAS extraction, but specifically from difficult matrices such as biosolids. So just as a little introduction, I'm going to talk about what sources of PFAS might be in the environment, how it may get into biosolid matrices and samples and why that matters, some of the analytical challenges you face with a biosolids matrix, and then a comparison of a couple of different extraction techniques that you could use on a solid matrix like a biosolid sample. So the release of PFAS into the environment has been studied for many years now. We understand the major sources, whether it be products like aqueous film-forming foams, also known as AFFF, or specialist products like PTFE materials and coatings which have waterproof, non-stick, or anti-stain properties. We also understand the direct sources of these products, from manufacturing of the coatings, released as effluent on site, to both the use of AFFF to extinguish fires and for training on airfields. The disposal of those products that can contain those coatings in landfills and recyclings can also be a source. However, non-point sources and other mechanisms of migration once the PFAS are within the environment, and any possible feedback cycles, whether it be natural or mechanisms influenced by human activity, still remain poorly understood. The issue we face with PFAS is their longevity when in the environment. Generally speaking, whilst there are variations based on chain length and chemistry, PFAS are highly mobile once in the environment, and they're not very reactive under normal environmental conditions and difficult to remove using the current technologies used for other contaminants in solid waste and wastewater. We also can't contain the contamination by isolating affected sites. Whilst there are known high-level areas, both globally and across North America, at this point, PFAS can be considered ubiquitous in the environment, having been detected in Arctic waters and both in air and precipitation samples. The figure on this slide shows typical sources and pathways within the environment and how they may relate to human exposure. In this presentation, we're focusing on biosolids, but there are many other processes and environments which need to be fully understood. Biosolids have been known to be a source for some time. Whilst PFAS can accumulate within animal and human bodies, a lot can pass through. The solid waste may be collected close to the source. For households, that might be a septic tank, or in the case of farms, left dispersed in the field, or collected in a central location. For municipal systems, these will all travel to a wastewater treatment plant where separated and pressed out as a solid waste, whilst the effluent water continues for cleanup before eventual release into surface water systems. The solid waste pressed out in wastewater treatment plants would accumulate pretty fast. So they have to be disposed of. That would normally be via dumping into a landfill site or spreading onto farmland, which has been common practice for many years. We can see that both these disposal routes can release large amounts of PFAS back into the local environment, where it can contaminate natural ecosystems or both pastoral and arable agricultural lands. In the case of landfill disposal, the PFAS can migrate outside the landfill site within leachate, which is processed again via a wastewater treatment plant, and again, either pressed out as a solid or eventually released into surface water systems. Biosolids can also be spread onto farmland, which is meant as a green and economical way to refertilize land used for agriculture. This unfortunately can create a feedback within the system, increasing contamination of food, which in turn would raise both human exposure and PFAS levels in future biosolid waste samples. So I think with that, you can see how important it is to understand this. But the issue is biosolids are a difficult matrix to analyze. They have unique interferences, which other study matrices like natural soils or aqueous samples such as surface water and drinking water simply do not have. So biosolids definitely require careful method selection, and that's what I'm going to talk to you about now. So biosolids, in essence, are a mixture of high organic matter solids and a varying level of aqueous content. They can also contain other contaminants from industrial sources that also pass through a treatment plant, and other components pass through bodies like proteins, lipids, or other fats, and all of that can cause issues with extraction and analysis. They can cause ion suppression during analysis. The other issue we have is there's currently not a published EPA method that deals with solids, and in particular not biosolids, which have unique challenges. The samples can vary sample to sample, both in components and also aqueous content. On top of that, each lab and regulator probably wants a longer list of analytes. Across the analyte list, you have different chemistries and chain lengths, which can alter how efficiently they're extracted from this difficult matrix. PFAS are also hydrophobic, so they tend to partition between the solid and aqueous phase, which can make them harder to separate. And they sorb to solid surfaces often quite well, including the glassware during extraction. So one of the best ways we can develop a robust method which can deal with these known matrix interferences is to use isotope dilution. I think many of you will know the principles of this, as it's widely used across research and regulation. However, I'll go through some of the benefits to a matrix like biosolids. In simple terms, isotope dilution involves the addition of known amounts of isotopically enriched standards to the sample. Ideally, the standards chosen are labeled isotopes of all the PFAS which are on the target analyte list. In the case of an isotope not being available for a certain PFAS compound, you would use an isotope that has a similar chemistry and should behave in a similar way in the matrix. The standards are always added at the start of any preparation. The sample is not manipulated in any way before the isotope goes in. The matrix properties and the extraction efficiency of the method used. In the case of biosolids, the suppression from lipids and organic matter in the sample and the difficulty removing the aqueous component would also happen to the internal standard. Also, because we're monitoring known amounts of standard, we can monitor the retention times and help predict any and qualify any retention time shifting of the target native analytes that may be caused by the matrix effects. Without this in place, it would be a subjective process of picking out the target analyte peaks. There's also an understanding that internal standard recovery is down to 10% are highly accurate and precise, and even below 10% may yield usable data when using isotope dilution. So now we know isotope dilution is key, there's other considerations we must take. As I mentioned on the previous slide, there's not yet a published method that focuses on solid extraction for PFAS, less so for biosolids. So there's no solid matrix gorilla available. The EPA methods published are 587.1, which is for potable drinking waters and is limited to 18 analytes. There's a new method 583 that uses isotope dilution. But again, it's for drinking water samples and is not for solids. So to use those methods, you have to build in a solid extraction before you continue the method. So you have to add a pre-extraction that would strip the analytes from the solid matrix, so you can then process it as an aqueous sample. There's also consideration whether you want to use wet or dry sample. You could air dry a sample or process both the aqueous and the solid at the same time. After you've done all that, you can follow the same tried and tested extraction techniques for PFAS using SBE, GCB for cleanup, and there's also lipid cleanup columns. So in this presentation, I'm going to briefly show you a comparison of two different methods. We tested air-dried versus a centrifusion separated biosolid sample. And we compared two different pre-extraction techniques of a simple methanol solid liquid extraction to an ion pair extraction. There are many papers detailing ion pair extraction covering many different reagent pairs, but for the purpose of this talk, we used the work by Zhang et al. 2018. The reference can be found at the bottom of the slide. An ion pair extraction causes the ionized analytes, in this case PFAS, into the organic phase by adding an oppositely charged ion into the matrix. It's been used for many decades on different combinations of ion pair reagents on different matrices and for different target analytes. This particular paper uses sodium carbonate buffer and a reagent called TBAS, which is tetrabutyl ammonium hydrogen sulfate. There are other digestion and pre-extraction techniques used beyond what is presented in this talk, but I just focused on these two. So in this graph, you can see the comparison of a simple methanol extraction versus ion pair in a biosolid matrix. You can see that on the shorter chain lengths from PFBA through to the mid chains, C6 and C8s, there are some comparable recoveries. I should say this is isotope recovery, not native analytes. But when you look at longer chains from PFAS down to the neutrals of methyl fossa and net fossa, you can see a much improved recovery from the ion pair extraction. This is because the ion pair extraction offers a kind of digestion of the solid matrix, whereas the methanol, you're just using an extraction solvent and you're not yielding the same recoveries. The longer the chain length, the more sticky it is to solid surfaces, including the solid and organic matter in a biosolid matrix. So now looking at a difference between a wet sample and an air-dried sample. The wet data is what we've just seen on the previous slide from the ion pair extraction. And then the same matrix air-dried and extracted again using an ion pair. Now there's across the board lower recoveries for the dried sample. I would expect some lower recoveries, but it's kind of interesting that everything was lower. When you dry a sample, you'd expect all the analytes in the aqueous phase to dry onto the solid phase and should be still extracted. Some of the shorter chains can be harder to recover, and there are some PFAS that are a little bit more volatile. But to have this across the board suggests that maybe there was a reduction in efficiency of getting it from the solid surfaces, including the container wall. And perhaps some more research needs to be done on how to improve this and to get reproducible results. But in this study, at least, it seems like processing a wet biosolid sample yielded better results and offered greater extraction efficiency. So in closing, and to summarize, contaminated biosolids are a significant source of PFAS to the environment. The way we deal with the solid fraction of biosolids means that it can easily re-enter into the environment via landfill leachates or spreading onto fields. Because of all the different interactions within a biosolid matrix, isotope dilution must be used to get accurate results. Wet samples seem to be better, to offer better recoveries than an air-dried sample. And aggressive digestion techniques such as ion pair works a lot better than a simple methanol shakeout. On top of all this, cleanup should be used at sample for all samples, all biosolid samples, and it should be sample specific. If you know there's likely to be high fats, you need to adapt your cleanup to remove those fat compounds. I think that's it. Thank you very much for listening to my talk, and I hope you enjoy the rest of the conference.